We're going to start now. Welcome back to this lecture. Last time, um, towards the middle, I tried to introduce um, the idea of eigenfunction of LTI systems, and which should have led led to the discussion of frequency domain. So this slide, which is the eigenfunction one, which is the property. So the idea is, if to an LTI system, if I input x of t, that's equal to e raised to s into t, which is an everlasting exponential, complex exponential. S is complex. S is any complex number of the type sigma plus j omega, and t is the time from minus to plus infinity. So if this is the signal that I consider, and I feed this signal to an LTI system, my question is, what will be the output? Okay, and this is what I was trying to do last time, and I made a lot of mistakes. Apologies for that. So this is quite easy to analyze, right? Let's say the impulse response is h of t, then y of t, you can write it as convolution of h with x I have the exact form of x here, e to the power of s into t. In place of t, you can replace this with t minus tau. So it is e raised to s t minus tau theta, right? And you can see that this exponentiation can be written as product e raised to s into t into e raised to minus s into tau. S into t comes out of the integration because it is only a function of t and not a function of tau. So you have e raised to st and minus to plus infinity h of tau e raised to minus tau theta. So this, if you look at the integration, tau gets integrated out because that is the variable of integration, s is the thing that remains. So this integration will be some function of s. S is the variable. So let us call this as capital H of s, simply because I'm taking h and transforming it. Okay. So if you call this as h of s, then you can see that my output is h of s e raised to st. So input is e raised to st and output is e raised to st. That is what is shown in this slide. So both input and output have similar frequency, have the same frequency, identical frequency, because s is a complex frequency. Then h of s defined by this integration is a scaling factor, and the scaling factor will be different for different s. For some s, h of s could be 0, for some s, h of s could be infinity, right? For things like oscillators which are working in a very high resonance area, the output amplitude can go very high, right? That is h of s can blow up, or for some frequency h of s can become 0. What is interesting about this is, for an LTI system, if the input is a certain frequency s, output will be the same frequency, right? That is the takeaway point, right? And that is the reason it is called an eigenfunction. So for an LTI system, e raised to s into t is an eigenfunction. If you input eigenfunction, you get back the same frequency except for a scaling factor. So I think I had made a mistake last time. I thought I will come back and correct myself today. And this h of s, which is defined here, is called transfer function because not the entire e raised to st comes out, right? It is scaled by a certain h of s. So that scaling function, so I am transferring some part of the input to the output, so it is called the transfer function. So it plays an important role in control systems and many other areas, including circuit analysis, circuit theory and so on. So we will not, of course, get into a transfer function, but nevertheless it is good to know what it is. Okay. So with that, we get now into frequency domain analysis. So, which is what I tried to do last time. I defined Fourier series in a certain way. I said the Fourier coefficients A naught, A n and B n could be calculated, and the reason they can be calculated are the cosine and sine have certain interesting properties. They are orthogonal functions. Cosine n omega naught t is an orthogonal set, meaning if you integrate each function it goes to 0 over one period. If you take the product, as long as n and m are different distinct frequencies, they integrate to 0. Cosine and sine set of functions are also orthogonal. So lots of interesting properties between that. I did not show them, I wanted you to go home and convince yourself, right. But anyway, using all of that you can compute A's A0, An and Bn. So that's the expression for the Fourier series. Cosine and sine can be combined using trigonometric relationships into a more compact form, right, where I have only one summation and instead of two summations. So every summation then has a Cn as the amplitude and frequency n omega naught with some arbitrary phase value theta n, right, and not very difficult to compute what is the value of Cn in terms of A's and B's and theta also in terms of A's and B's, right. So because I now have just one term for each frequency, right, C1 if the frequency is omega naught, C2 if the frequency is 2 omega naught and so on. So I can now talk in terms of the Fourier spectra. I will come back to that point later, right. So a Fourier spectra can be defined. So another compact form is possible called the exponential Fourier series, where I express x of t in terms of an infinite sum going from n going from minus to plus infinity. Xn becomes the Fourier coefficient, and instead of sine and cosine I now have e to the power of j n omega naught t, where n omega naught is the nth harmonic of the fundamental frequency, right. And it is also possible to compute xn is given by this simple relationship now 1 by t naught integration of x of t and its product with e raised to minus j n omega naught t, right, over one period. So this is a very compact form, right, and relationship is quite easy because just like cosine and sine functions are were an orthogonal set, e raised to j n omega naught t, this set of complex exponentials, everlasting complex exponentials are also orthogonal. This forms a very good interesting set of functions for us, given the fact that we had defined eigenfunctions of LTI systems in a certain way. So that is the reason why I quickly gone from sine cosine to e to the power of j n omega naught t, right. And you can use the Euler's relationship to go from one to the other. If you have the trigonometric relationship, from there you can generate the complex exponential relationship, right, and I'll skip all this. Okay, so then I tried to use the Fourier series ideas on a problem, right, a problem which is made up. It is there in the textbook that we have been talking about, and I've just taken from the textbook. So where a function e raised to minus t by 2 defined between 0 and pi, right. So its value at t equal to 0 is 1, its value at t equal to pi is e raised to minus pi by 2. This basic time limited exponential function repeats, right. So I repeat it every pi seconds. So infinite number of times in both the directions. So because this basic function repeats, this is a periodic function. So x of t is periodic. It satisfies my definition of periodic function that I did last time. So given this periodic function x of t, can I find the Fourier series, right, and Fourier series definition is given here. Can I find xn, capital Xn, right? You can start from the definition of xn and go on substituting for x of t from over one period, and xn can be computed to be something like 0.504. That's an approximation because 0.504 comes from that complicated relationship 2 by pi into 1 minus e to the power of minus pi by 2, right, and that comes to 0.504. You can check it out. denominator is 1 plus j 1 plus j 4n. So it's a complex. So xn is complex. So if you substitute for xn in that infinite sum, x0 you make n equal to 0, so it's only 0.504, x1 x minus n, x minus 1, x2 x minus 2 and so on. So you can expand that and write x of t in terms of individual frequencies. So notice that xn and x minus n are complex conjugation of each other. So whenever x of t is a real signal, which is in this case, xn and x minus n are complex conjugation of each other. This property is called conjugate symmetry. It means magnitude of xn, because z and z complex conjugation have the same magnitude. So the magnitude is even symmetric, n minus n has the same magnitude, and the phase is odd symmetric, right. We will come back and describe what is this even symmetry and odd symmetry. That is the property of all real signals. I have terms like, in this expansion you see that the second term is e to the power of j 2t. So the frequency is 2, right, and the third term is e raised to minus j 2t. So the is the frequency minus 2. I put on the question there. I should have put that question in red, right. Can the frequencies be negative? This is where I had left last time. So I told you that frequency is a count, right. I mean, it's like when you bounce a ball, right? How many times the ball goes up and down per second or per minute or per unit time, right. So the count cannot be negative, but count can be 0. I mean, if you stand for election, right, I mean, the worst case is you will get 0 votes. There is no negative votes, right. So count can never be negative, or a frequency can never be negative. I am not talking about complex frequencies. So this is a real frequency, right? So it's just that the Euler's relationship, make cosine expressible in terms of e to the power of j omega and e to the power of minus j omega, but the frequency is positive, right? So there are no such thing as negative frequencies. Nevertheless, when it's nice to deal with complex spectrum where I have positive and negative frequencies. So only in the complex spectrum, only when I talk about complex frequencies, positive and negative frequencies make sense. Otherwise, frequencies by itself, right, is a positive or a non-negative number. So I continue with the same problem. I have now in the I want to sketch the spectrum of my example problem. X of t is written in terms of its Fourier coefficient 0.504 by 1 plus j 4n, that is the xn, and e to the power of j n omega naught t. In this case, omega naught is 2, right? So it's 2 nt. So n can take value 0, in which case it is constant. N can take value 1, in which case the frequency is 2. N can take value minus 1, the frequency is still 2, and so on. So below I have shown two sketches, one for the magnitude of xn, because xn is complex. So what I have done is, so I have xn as 0.504 by 1 plus j 4n. Is it 4n? Yes, 4n, right. So this is complex. So I have now sketched the magnitude. Magnitude of this is 0.504 1 square plus 16n square under root. That is the magnitude. Is that okay? A square plus b square. So 1 square as it is, 4n square is 16n square. From here it's clear that whether n takes positive or negative value, because I have n square here, it does not matter. Whether n is minus 1 or plus 1, n square is independent of the sign. N is 2 or minus 2, n square removes the effect of the sign, and so on. Okay? So that is one explanation I want you to see. And the second explanation is, when n is, let us say, 4 or greater, n square is already 16. 16 into 16 is 256, right. For n equal to 4 or greater, this is so much bigger than this. 16 n square is so much bigger than this, right. this has no effect. So you could write this as approximately 0.504 by 4n when n is greater than, let's say, 3 or 4 or something. Is that okay? Effect of 1 can be removed. I am left with 16n square under root, that's 4n, and so that's positive part. So that's the magnitude. And second thing is I have its phase value. Phase value is numerator is real, so contributes nothing to the phase. Denominator is minus tan inverse 4n. It's 4n by 1, doesn't contribute anything much. So if n becomes large, say n is 4, then tan inverse 16 is nearly, tan inverse of large number is pi by 2. So when n is positive, this quickly tends to minus pi by 2 for n greater than 0, plus pi by 2 for n less than 0, because if n is 4, tan inverse 16 is nearly pi by 2, and there is a negative sign here, so it's minus pi by 2, which is what I've tried to show, a sketch in the spectrum, right. So I've now plotted instead of taking n, I plotted in terms of omega, right. So my omega naught is 2, so I get values at n equal to 0. There is a, so if you substitute n equal to 0, n equal to 0 here, it's 0.504. So that's the first magnitude, that is x0. X, you substitute n equal to 1. For n equal to 1, the frequency is 2, so I have a value at 2 radians per second, and that is, so n equal to 1, so n equal to 1 would be 16 plus 1 is 17, nearly 4, right, nearly 4. So 0.504 by 4 is something like 0.104 or something. So I have that there. So you see that I have 0.504 by under root 17, that is 16 plus 1. N equal to 2, frequency will be 4 radians per second. So n equal to 2 will be 2 square is 4, so it is 64. So under root 65. So you see that I have there under root 65, 0.504, and same value repeats at n equal to minus 2. So you can go on sketching, right? You can go on sketching the magnitude. So this is 0.504, and this is omega axis at omega equal to 2 some value, at omega equal to 4 some value, and omega equal to 6 some value, and so on, and even symmetry because of this. So this is minus 2, minus 4, this height is equal to this height is equal to this height. So that's the magnitude of the Fourier coefficient. You can also sketch the, so below this you can sketch the phase value, that is at n equal to 0, this value is 0, because tan inverse 0 is 0, so that's a 0. N equal to 1, that means omega is 2, right, n equal to 1, tan inverse 4, and tan inverse 4 is nearly pi by 2, little less. I have the I have not shown the value. So at this, because of the minus sign, somewhere here is minus pi by 2. So at 2 is nearly pi by 2, not quite, but there. At 4 you are almost there. At 6 you are caught up with pi by 2 completely. So that's minus. For n equal to negative, flipping takes place. So the phase is odd symmetric. This is even symmetric, this is odd symmetric. Some value here at minus 4 is this. Once you have the Fourier series coefficients, you can sketch the magnitude, and for real signals it will have even symmetry. You can sketch its phase. For real signal it will have odd symmetry. Right? That's the idea of a conjugate symmetry. Okay. So let's take one more example. Right? I've taken a regular rectangular pulse, that is 1 for some time, 0 for some time, 1 for some time, 0 for some time, and goes on and on and on in both the directions towards infinity and negative infinity. Right? In this case, you can see that I've selected period. So my period is from this midpoint, so here from minus pi to plus pi. So period is 2 pi, period is 2 pi, and frequency in hertz is 1 by T naught is 1 by 2 pi hertz, right, and frequency in radians is 2 pi f naught, so it is 1 radian per second. So for this particular problem, where I have a rectangular pulse oscillating between 1 and 0 with periodicity 2 pi, that means frequency is inverse of that when frequency expressed in terms of hertz, so it's 1 by 2 pi, and frequency in radians is 2 pi f naught or 2 pi by T. That's another way of writing this, same thing, not different at all. T naught is 2 pi, this is 2 pi, so it's 1 radians per second. This is what I've tried to say right in the text here. So T naught is 2 pi, f naught appropriately 1 by 2 pi, and omega naught is 1 radians per second. So I want to express this as a Fourier series complex exponential format, right. So x of t is given by xn e raised to j n omega naught. Omega naught is 1, so it is simply n t. So omega naught is already captured, omega naught is 1, so I don't need to say it separately. So normally I would have written it as e to the power j n omega naught, but omega naught is 1 here, so it's j n t. So I want to compute what is xn, find out what is xn for this. So by definition, xn is 1 by T naught integration over any one period, doesn't matter where you start, right, and you take x of t e to the power of minus j n omega naught is 1, j n t dt. Carry out this integration. I think this is what I have tried to do here. I have not shown the steps. I would like you to go home and try this. Substitute for x of t from one period, so it means you start at minus pi, right, it's 0 up to this point, then it is plus 1 up to from minus pi by 2 to plus pi by 2, and 0 up to plus pi, right. So substitute that, carry out the integration, and show that xn, right, has a very interesting shorthand description. It is half for n equal to 0, right, and 1 by n pi sine n pi by 2 for other values. Otherwise, looks mysterious right now because I have not shown you the steps. I want you to go home and try these steps. Okay, so that's very easy. Substitute for x of t. X of t is 1 between minus pi by 2 and plus pi by 2. So lower limit minus pi by 2, upper limit plus pi by 2. Xt is 1, so you don't need to substitute, and integrate e raised to minus j n t for that, and because it's pi by 2 and pi by 2, you get sine n pi by 2, and appropriately this n comes in the denominator, and that's how, and t naught is 2 pi, right, and that contributes a pi here. Okay, so you get sine n pi by 2, and now it's extremely simple. If n is 3, sine 3 pi by 2 is 0. N is 5 pi by 2 is 0. So for all odd values, if n is even, sorry, if n is even, right, n is 2, sine pi is 0, n is 4, sine 2 pi is 0, n is 6, sine 3 pi is 0. So for all even values of n negative or positive, doesn't matter, for all even values of n, this goes to 0. So this exists, the Fourier coefficients exist only for odd values, and when they exist, you see that when n is 1, sine pi by 2 is 1, n is 3, sine 3 pi by 2 is minus 1. So they change sign alternately, minus 1 plus 1, minus 1 plus 1. So very easy to see that in this case x0 is half, already shown here, x1 n equal to 1. So this is 1, numerator is 1, denominator is pi, so it is 1 by pi. Similarly x minus 1, n is minus 1, so sine minus pi by 2 is minus 1, there is a minus 1 here, so it is again 1 by pi. So both x1, x minus 1 are 1 by pi. Unlike the previous example where xn was complex, here xn is real, and x2 is 0 because you substitute n equal to 2, so sine pi is 0. Similarly x minus 2 is 0. x3, substitute n equal to 3, 3 pi by 2 is minus 1, so it is minus 1 by 3 pi. This becomes minus 1, this n is 3, so it is n with 3 pi, and x of minus 3 is minus sine 3 pi by 2, so that is minus 1 minus 1 minus becomes plus 1, so it's there is a minus 1 here, so it is 1 by 3 pi and so on. x4 is 0 and so on, right, x minus 4 is 0, okay, and so on. So you can go on, adding them up. So that is what I try to do here. I will now expand, right. I substitute all these values in this, right, and I have the first term here given by x of t is half, because x0 is half. So in this case substitute n equal to 0, this becomes 1, so half. So that is my first term, that is half, right, and substitute n equal to 1, n equal to 1 is 1 by pi, so I have here 1 by pi and e to the power of j, n is 1t, and similarly substitute n equal to minus 1, that is 1 by pi e raised to minus jt, right, and similarly you substitute n equal to 3 and so on, because x2 is 0, x minus 2 is 0, and so if you collect these terms, let me just write in this case expanded, let me write x1 e raised to j t plus x minus 1 e raised to minus jt, this is 1 by pi, so 1 by pi e raised to jt plus e raised to minus jt. I can use Euler's formulas to write this as, right, this is 2 cosine t, okay. So both 1 and minus 1 combine to give me 2 by pi cosine t. That is what I am going to do next. So collect terms of equal powers of exponentiation and join them. So for the rectangular pulse periodic signal x of t shown on the top left by that red curve, I now have a compact Fourier expansion, right, in the trigonometric form, because exponential is slightly difficult, trigonometric form. So it is 1 by 2, that is because of this, and combine to give me 2 by pi into cosine t minus 1/3 cosine 3t plus 1/5 cosine 5t and so on. That is again an infinite series, right. And before I take a break, I'll just tell you one interesting application of this, because infinite series, I told you, are always mysterious, right? I mean anything infinite is beyond our imagination. So many people have spent a lot of time looking at infinite series. Srinivasa Ramanujam is definitely one of them, right, or you can think of him as the god of infinite series. So this is an infinite series. So what I can do next is, if you substitute t equal to 0, what is the value of x of 0? Look at this. In this case, if you substitute t equal to 0, x of 0 is 1. Right? So on the left hand side, if you substitute t equal to 0, then x of t is equal to 1 on the given function. On the right hand side, if you substitute t equal to 0, cosine 0 is 1, cosine 30 is 1, cosine 50 is 1, right. So all these cosine terms, this becomes 1, this becomes 1 but divided by 3, this becomes 1 divided by 5 and so on, which is what I try to show next one. So you substitute t equal to 0, then you get a nice theorem that says 1 minus 1/3 plus 1/5 minus 1 by 7 and so on, right, will give you pi by 4. I mean, amazing, right? You could not show it any other way. I mean, if I ask you to show that this infinite series converges to pi by 4, right? So this is one quick way of getting pi by 4. 1 minus 1/3 plus 1/5 minus 1 by 7 and so on, so on, so on, right? You get pi by 4. So I think this is a good time to take a break. Please ask questions. So take some time off, and we'll take questions now. Okay, so the question has come from PhD Tech. Okay, thank you, PhD Tech. Sine t and cosine t differ just by 90 degrees in trigonometric Fourier series. Is it enough to only find coefficients of cosine t? What is the need to find sine coefficients too? I think you are right when you say that sine and cosine are not very different. Right? If you take cosine, shift it by 90 degrees, it becomes sine. Right? If you take sine and push it back by 90 degrees, it becomes cosine. So sine and cosine differ only in phase. That's an important idea. Right? You are right in your statement that sine and cosine differ only in phase, and that is the crux of the matter. Because let me go back to this problem. I can show you in how many different ways I can draw this problem. The example I solved is like this. This is what I solved. You can see by PDF file. The nice thing about this is even symmetric. The example I solved, go back and check, is even symmetric. Nothing prevents me from moving the origin to the left or to the right. I can make it look like this. Right, like this. So this signal and this signal are identical in every respect except for the origin. The origin here makes the signal symmetric. The origin here makes the signal look very different. Well, there is an odd symmetry if you shift the y-axis little bit, but this and this look very different. Correct? So the two signals are identical, but just because the phase are different, they look very different, and I can even make them look worse. If I draw the y-axis in between in a very asymmetric way, right? Whatever symmetry was here, little bit was left in this. Now there is no symmetry in this problem at all. So just by changing the phase, I can get signals which look very different. So I need to have both sine and cosine terms adding up in different proportions, okay, to make up all these situations, right. My hunch is because this has even symmetric and cosine has even symmetric, in this expansion only cosine terms will be there if you go back to the trigonometric series, right. So if you go back and check, this expansion will have only cosine terms. This has an odd symmetry like sinusoids. So in the expansion this will only have sine terms, there won't be any cosine terms, whereas in this case both sine and cosine terms will be there. So they give you different phase. So the reason I have both sine and cosine terms is to take care of this phase, whatever be the arbitrary delay, right, and sine cosine terms contribute to that. Thank you for the question, very good question. So question from PCPY, which is the suitable tool for digital signal processing? Is it Fourier series or is it Fourier transform? Okay, everybody is getting ahead of me. I have not talked about Fourier transform here at all. I'm going to come to it. So please have patience. Today or in my last class next week, I will talk about a Fourier transform. At that time you can ask me this question, right. So let me first introduce Fourier transform, then you can ask me. PCPY, what are the applications of Fourier series? Lots of applications. right. I already showed you one application which is an infinite series. Right. If I ask you to show, does the series 1 minus 1/3 plus 1/5 minus 1 by 7 and so on, does it converge? Without Fourier series, I can bet my bottom dollar that you cannot show. What is the application? Definitely in the convergence of infinite series, Fourier series is the grand tool. Okay, that shows now the convergence of this series. Lots of tools. I mean, the idea that you can break up Fourier series, you can break up periodic signals into Fourier series itself is a fundamental idea, right? That has led to the development of DFT, FFT, and so on, which we study in digital signal processing, right? So the entire transforms theory, right, is based on Fourier series and Fourier. Lots of ideas in communication where we do orthonormal Fourier series, orthonormal expansion are based on Fourier series. Right. So today, if you are able to do digital communication, is because of Fourier series. So Fourier series starts at the very heart of uh, modern day communication, right? Whether it's OFDM, whether it is standard digital communication, everywhere, Fourier series is the basis, right? Without Fourier series, we couldn't have made any of these things possible. I mean, whether you go for ECG and so on, right? So wherever frequency transforms are applied, Fourier series is the basis of all that. That's at the very heart of it. Question from GIT Jaipur: why we cannot directly calculate the Fourier? Why we cannot calculate the Fourier transform of unit step signal? Okay, I will not answer Fourier transform right now. Okay, I will keep that in abeyance. I'll come back to it when I talk about Fourier transform, right? So please hold your questions till then on Fourier transform. Because to calculate a Fourier transform of step signal, we have to use signum signal. Maybe uh, we electrical engineers are not mathematically very precise, right? We do lots of operations which will scare the mathematicians, right? Mathematicians want precise logic, they want precise reason why something is being done, right? And we electrical engineers, don't care for all this precision. As long as it works, it's okay, right? So one such application is this signum thing used to calculate the Fourier transform of unit step and so on. Okay, I'll come back to that. That's by doing that, I think electrical engineers are avoiding lots of problems inherent in mathematics, right? Inherent in our understanding of mathematics. Okay, so that's a trick we use. Mathematicians don't like tricks, right? Mathematicians go strictly by logic, right? We electrical engineers have reduced mathematics to tricks. Right? So these are some of the tricks that we have employed, right, in order to make these ideas easily understandable. But please understand that impulse is not your regular function or a regular signal. Unit step is not your regular signal, regular function, and similarly signum also is not your regular function, right? We deal with regular functions, and whatever analysis we have for regular signals, we have extended that to include all these things, right? And so if you strictly go by the ideas of existence, which I'm going to talk about soon, um, uh, an impulse function is not a regular function, right? And it does not have Fourier series or Fourier transform. But nevertheless, we go ahead and apply all these things by taking limits and so on, right? So it's something that oftentimes the tragedy is electrical engineers reduce some of these complex mathematical ideas to tricks, right? Because we want to apply that to real life signals, and real life signals are not like impulse, are not like unit step, are not like signum function and so on, right? And so then it's at the level of tricks, right, not at the level of theory. Question from CIT: how does E of t okay, 0.504 becomes 0.044 n. Okay. So I wrote here that good question. I may have missed out something there. So I wrote xn as 0.504 by 1 plus j 4n. Right. This is the calculated value of the Fourier series, Fourier coefficients. Then I wrote xn magnitude as 0.504 because that number is positive. So I take the number as it is. Denominator is real plus imaginary. So a square plus b square under root, a square plus 16n square under root. Because it's magnitude, I always look at the positive number of the square root. In this case, interestingly, whether n is positive or negative, n square is always positive. So I don't need to worry about the sign too much. But when I make approximation, when I said n is some value something like 4 or minus 4, then this is so much bigger than this that one can be ignored. Right? I could have written this as 0.504 by 4n. Ignore this, I get 16n square. Take root. Strictly speaking, it is plus or minus 4n. Yes, it should have been plus or minus 4n, but I am looking at the magnitude. So just to be consistent, I wrote this as magnitude because n can be negative, right? So in this case, if n becomes minus 4, then the magnitude, I am afraid, can become minus, so it becomes inconsistent. So just to retain the consistency, I put magnitude. I think that was the question. Good question. Okay. From VCE, why always it is easy to analyze the circuit in frequency domain than time domain? Why don't we prefer time domain analysis? Actual circuit analysis, right? Actual circuit analysis using large packages like PSpice and so on. They actually do analysis in time domain. A combination of time and frequency domain is always applied. It is never purely time domain. It's never purely frequency domain. Right? In order to solve real life problems, I mean, you have to understand this idea at a very early stage that when we teach circuits like resistance and capacitance, I mean, in the textbook at most we have 3-4 resistances, a few capacitors and a few inductors, right? The number of elements I can draw on the board is never more than 5 or 6 or 10. Actual circuit contains lakhs and lakhs of components that neither can I draw nor can I analyze, right? So please remember that we talk about extremely simple things in classrooms. Okay, actual circuits are much more complex, right? I can draw 4 or 5 resistances and which I can analyze very well, but the actual analysis required for real life problem, whether it's your entire electrical grid or whether it's a microprocessor or any analog circuits, HOD converter, I mean, it contains thousands of elements. And so you have to understand that we are solving extremely simple problems in the class just to get the idea across. Real life problems, what the engineers out there do, are really complex. So they employ time and frequency domain analysis. SPICE is one example of that, where you can define thousands of elements and analyze them in time domain. Okay, so let's get to this. So I have I've taken the same example shown now in a bigger picture occupying the entire slide, the same rectangular periodic signal with period minus pi to plus pi, right? Please remember this has discontinuities. At minus pi by 2 there is a sudden jump. It was 0 before minus pi by 2, after pi by 2 it becomes 1. So there is a discontinuity. At plus pi by 2, before pi by 2 it was 1, after pi by 2 it is 0. So again there is a discontinuity. So this x of t has many discontinuities, and I told you that when Fourier presented his paper and he claimed that any periodic x of t can be written in terms of summation of sines and cosines of fundamental frequencies and harmonics, that paper was thrown out. Poor Fourier died without publishing his paper. It took another 60-70 years to understand in what sense x of t is equivalent to what we write on the right side. Right? So the thing called mean square sense and so on. So in the convergence series, in what sense the two are equal? The left side is x of t, right side is infinite series. In what sense they are equal? Right? Forms a very interesting topic in mathematics, and for them to understand the problems that Fourier talked about, it took 70-80 years. Then they accepted Fourier's analysis, right. So the reason why his paper was thrown out was x of t shown there cannot be differentiated for all values of t, because at t equal to minus pi by 2 there is a discontinuity. I cannot differentiate it there. At t equal to plus pi by 2 there is a discontinuity. It cannot be differentiated there. Whereas on the right hand side I have sine and cosine which can be differentiated any number of times, infinite number of times, extremely smooth functions. So that is the reason why the mathematicians during Fourier's time did not accept Fourier series. Right. Around 1900s, when the idea of convergence, which is why when I say it is the time of Srinivasa Ramanujam, that is when they accepted in what sense the left and right are equal. Okay, so I will briefly mention that by a very famous idea called the Gibbs phenomena. Right, Gibbs said, okay, let us assume Fourier is correct. Right, so Fourier is correct. So in this case, I had x of t equal to half plus whatever I wrote 2 by pi into cosine t minus 1/3 cosine 3t plus 1 by 5 cosine 5t and so on. So let us take this infinite series. On the left hand side I have x of t given by the rectangular signal. Suppose I take only the first two terms, left hand side be equal to the right hand side. If I take one more term, what happens? If I take 20 terms, what happens? If I take 50 terms, if I take 100 terms, what happens? Right? So I guess 100, 150 years ago, when you didn't have computers and calculators and so on, people could spend 5-6 years doing their PhD on this. If I take 5 terms, what happens? 20 terms, what happens? And so on. I mean, today it is to me it's a matter of seconds to tell you what it is, which is what I've tried to do next, right. I've now sketched here what happens if I just consider half plus 2 by pi cosine t, shown there by black, right, yeah, black. So I said n equal to 2. If I take 2 terms, what happens? If I just take this, and it's very clear that the red and black are very different, right. How many times do they converge? How many times are they equal in one period? How many times red and black meet in one period? They meet at some point between minus pi and plus minus pi by 2, right, between. So they are meeting here, they are meeting here, they are meeting here, and they are meeting here. So exactly 4 locations in one period they meet. For all other values, this and the 2 terms are not equal, correct, right. So convergence fails for all times. Convergence happens only for those 4 values. Okay. If I now take 3 terms, so if I take one more term, now shown by what color is this? I think it's blue color, right. Look at the blue color. The number of times they meet is more. Just like I showed for black and red meet 4 times in one period. Now red and blue meet more number of times, right? So you can now go on adding, right? So I have now added 11 terms, right, gone up to 11 terms in this, and I get a kind of a sea blue color, right? Not quite visible here, but still they only meet a finite number of times. Between minus pi by 2 and plus pi by 2, I have infinite points because x of t is continuous, whereas whatever number of terms you take, you only meet so many times, right. In plus 1, if you take 11 terms, it goes up and down 11 times, they only meet 11 times. If you take 100 terms, they only meet 100 times. If you take 5,000 terms, you only meet 5,000 times, but not all the time. And interesting part, many people noticed, no matter how many terms you take, the peak which is above 1, right, if you go back here at t equal to 0, when you take only 2 terms, black is above red by a certain value, right, whatever is that value, whatever it's 2% more or 5% more, interestingly that remains. You always get at some point that much more, 5% more, right, at the extreme points. So that's what is called the Gibbs phenomenon. Gibbs said it doesn't matter how many finite number of terms you take in this series, that number of terms, the peak which is always greater than red value will be whatever 5%, 2% of that, and he calculated it, I mean, and showed that's how it will be, right. That's the convergence of series, okay. So and you can see that no matter how many terms you take on the right hand side, you will never converge to x of t everywhere. If you take 50 terms, it converges to x of t 50 times, right. So then in what sense is this equal to this? So they said you look at the difference between this and this, you consider n terms, look at the difference and square the difference, because the difference can be positive or negative. You square the difference and integrate, you find the energy of that, right, or in this case it's a power signal, so find the power of that. That power goes to 0, right. So they said this convergence is in the mean square sense, not convergence in the mean. Convergence in the mean means both are equal everywhere, right. So this equivalence the Fourier series talks about for some discontinuous signal is mean square convergence and not the convergence in the mean. So all these ideas took lots of time, 70-80 years after Fourier died, right. So now we understand that the two might be equal in some sense. Then the question is, can I write Fourier series for any periodic signal? Okay, and again in around 1900, a French mathematician by name Dirichlet, he said if the function x of t satisfies a certain number of properties, then you can find Fourier series. So the properties are listed here. I am not going to go through them or explain or give you counter examples. It says x of t must be a power signal, right. It must be absolutely integrable, meaning it should go to infinity in one period, it should go to infinity, right? So it should be absolutely integrable. If it has discontinuities, the number of discontinuities should be finite in one period, and our rectangular thing has 2 discontinuities, so finite number of discontinuities. The number of maxima and minima in one period should be finite. So there are some complicated mathematical ideas, I am not going to get into them. If you leave it to me, most of our signals satisfy Dirichlet conditions. We deal with ordinary power signals, we deal with signals that do not have infinite number of maxima minima, do not have infinite number of discontinuities. So we have well formed signals, right. So these are the mathematicians trying to really understand, right, in what sense they are equal. So they are the ones who come up with all these existence conditions. So I am saying that practical signals, the signals that we electrical engineers are called to work with, they satisfy Dirichlet conditions without any problem. So they are square integrable, they are energy or power signals, right, and they satisfy all these conditions. So we don't really have to worry about this. Now comes the energy theorem that somebody asked, power spectrum. You can show that the power of this periodic signal x of t, yeah, I'll do this and take a break. So what I have here is the definition of power that I gave in my very first class, right. Power of a periodic signal is its integration over one period, square and integrate over one period, divided by the time is the power, and you can show that that's equal to summation of xn magnitude square. Xn is the nth Fourier series coefficient, 1, 2, 3, minus 1, minus 2, minus 3. So if you add them up all, infinite sum, that will be equal to power. So this gives me a sense of how frequencies are distributed in power. xn is some kind of an amplitude, right? Xn square gives me the power. So this is the power spectrum, right? If you now sketch it in terms of the spectrum, have x axis as omega and xn square magnitude on the y axis, right? That is the power. And because xn and x minus n are complex conjugation of each other for x of t real, this Parseval's function can be further simplified, which is what I have shown there, that power contained in the signal x is magnitude x naught square plus 2 times, now summation going only from the positive time, n equal to 1 to infinity xn square. So you know, interesting application. Let's look at one application of this and then take question. The signal I had was minus pi plus pi minus pi by 2 plus pi by 2. This is my x of t and the value is 1 here and 0 here. This is one period. So its power of x is 1 by t naught is 2 pi, in this case minus pi by 2 to plus pi by 2, x square is 1 dt, so it is 1 by 2 pi into pi, so it is half. So this signal has power equal to half, this signal has power equal to half. But if you go back and look at what value we had for xn, right? So we had xn equal to half for n equal to 0, 1 by n pi sin n pi by 2 otherwise. So and I said that whenever n is even, this goes to 0, n 2 goes to 0, 4 goes to, so only defined for odd values, and for all of them it is either plus 1 or minus 1. So if you tell me what is xn square, right, xn square will be summation xn square will be, you know, 1/4, because x0 square is this, plus 1 by pi square n equal to 1, this is plus 1, and minus 1 will be 2 pi square, okay. N equal to 2 will be 0, n equal to 3 will be minus 1 by 3 pi, so it is 2 9 pi square. Similarly, so this is 3 square, this is 5 square, and so on. So if you now take it out 1 by 4, and you know that its power is equal to half, so 2 by pi square is 1 plus 1 by 3 square, 1 by 5 square, 1 by 7 square, and so on, right? And so you get this relationship, half minus 1/4 is half, so it is pi square by 4 is 1 plus 3 square, 1 by 5 square, 1 by 7 square. We got another, you know, excellent infinite series as one application of Parseval's formula. Okay, so we'll take a short break now. Please ask questions. Right. So lots of applications of this also. Right. So is this okay? So you know, you can now take this and write it in many different ways. So the Parseval's gives you one more way of combining exponential infinite series. Thank you. So this is the question time. Take. I have. It's okay. Oh, don't worry. It's only tea. I'm not giving any snacks or anything. I'm just giving you tea. So half minus 1/4 is 1 by 4. Oh, sorry. It's pi by 8. So it's pi square by 8. Okay. So the question is how to draw power spectrum for the problem. Good question. Okay. Let me take that question now. So what does it mean here? So I can draw xn magnitude square. Okay, xn magnitude square. I am putting omega here. Remember, in this case, t naught is 2 pi, f naught is 1 by 2 pi, and omega naught is 1. Right. So n equal to 1. I have omega equal to 1, n equal to 2 I have omega equal to 2, n equal to 3 I have omega equal to 3. So first is you make n equal to 0, n equal to 0, so this is 1/4. So 1/4. Remember the total power is half, right? In this case total power is half of that is present in DC itself. So that's then n equal to 1, n equal to 1 is 1 by pi square, right? I have combined two terms here, n equal to 1 and n equal to -1, right? So it's 1 by pi square in +1, 1 by pi square in -1. So pi square is nearly 10, so 1 by pi square is 0.1. So this is 0.25, this is 0.1. 1 by pi square, 1 by pi square. So I've indicated power present in each of the component frequencies. In between it has no values, other frequencies power is 0. N equal to 2, n equal to 2, what is it? N equal to 2 is 0. Substitute n equal to 2, this is 0. So there is 0 power here, 0 power here. N equal to 3, right? It is 1 by 9 pi square. Pi square is 10, 1 by 90, 1 by 90 is 0.01. So 1/10 of this, right? So it is 1 by 9 pi square. Similarly, a 3, oh sorry, what did I write? 1 by 9 pi square, 1 by 9 pi square, and so 4 is 0, -4 is 0, and so on. So I can now write, so power spectrum tells me how much power is contributed by each of the complex frequency terms. So the total power in the given signal is half, of which 50% is present in DC itself, and the first harmonic or the fundamental frequency contains significant amount 0.1, 0.1. So this is 0.25, 0.1, 0.1 is already 0.45, right? Total power is 0.5. So I'm already closing the gap, and all other ones, all even terms contain 0 power, all odd ones contribute some terms, and they contribute less and less as the frequency increases. So this is the power spectrum, tells me how the power is distributed in various frequencies. Live interruption, okay, very good. Live interruption. Okay, so I have a live interruption, very good, from PCTN. I think please ask the question, whether convolution property applicable in Fourier series. I don't know what you mean by that, convolution property. I said you cannot convolve two infinitely long power signals, right? Because convolution of course is an integration, that integration does not exist, right? So only when that integration exists. So remember, before you do anything, if you are dealing with integrations where the limits are plus or minus infinity, you have to take a pause, right? These are not normal integrations. Similarly, infinite sum are not normal sums. You have to know whether it converges or not. Only if it converges, it exists. So if you take two infinitely long pulses and convolve, it may not converge, and so the convolution is not defined. So you have, these are all what are called improper integrals. So if it is improper integral, then you have to take lot of care before you can answer that question. Give a simple example of an analog periodic signal which is not absolutely integrable. Okay, so the question is, can you give a simple example, right? I cannot give a simple example, right? The reason is, the signals we study, the signals we are interested in, the signals we see in nature, they are all normal signals, do not exhibit abnormal properties, meaning they do not go to infinity, right? They do not have infinite number of discontinuities, meaning they do not have infinite number of maxima and minima within a period, okay. So I cannot give an example. However, this kind of questions delights mathematicians. They will spend their life in trying to come up with a counter example, right? Nothing pleases a mathematician more than saying your theory doesn't work on this, right. They will spend lots and lots of time, right. So this question is, the question you asked is a theoretical question, is a mathematical question. I will not be able to answer that question. Give a simple example of analog periodic signal which is not absolutely integrable. Yes. Can Fourier series expansion be applied to non-periodic signals? So that's a question of Fourier transform. I'm going to come to that. Okay, I'm going to come to that. So now let me go back. Um, um, okay, I answered how to draw power spectrum. I've answered why we cannot directly calculate Fourier transform of unit step signal. I've answered can Fourier series expansion be applied to non-periodic signals. Okay, so with that I will go back, and now as I told you, I am not interested in making this lecture into a Fourier series lecture. I am not interested in making this into a Fourier transform lecture. Okay, my objective is limited. In LTI systems, I am studying LTI systems, right. In LTI systems, why should I study Fourier series? Why should I study Fourier transform? So my objective is extremely limited here. Okay, so I am not going to get into properties of Fourier series and so on. I may have mentioned a few properties in passing, right, but that is not exhaustive. So let me now go back to LTI systems. Okay, my objective is go back to LTI every time. So what is the importance of Fourier series in the context of LTI systems? Let me go back and look at the eigenfunction of LTI systems once again. So what I said then was, if you have an LTI system of some impulse response h of t, and the input x of t is an everlasting exponential of the form e to the power of st. LTI system is the first requirement, and input now is a specific input e raised to power st, everlasting, meaning it goes on and on and on from minus to plus infinity. For such an input, I said output y of t is given by h of s into e to the power of st. Same function comes at the output, and h of s was defined as transfer function. It is h of t e raised to minus st dt. This is h of s. So I said for LTI systems, e raised to st is an eigenfunction. Eigenfunction meaning when you give this input, I get the same at the output. I am giving this input, I get the same at the output. Maybe there is a change in the scaling factor. If I feed in 1 volt, I will get there half a volt or 3/2 of a volt, right. But same frequency, if I feed in 50 hertz, I get 50 hertz. If I feed in 100 hertz, I get 100 hertz. Frequencies do not change. Scaling factor can change. Scaling factor can be positive, scaling factor can be negative, scaling factor can be less than 1, scaling factor can be greater than 1, scaling factor can be 0. If I feed in a certain frequency, output can be 0, that is acceptable. That means same signal but with 0 amplitude. So for the LTI system, when I feed in a certain frequency, output can be, there are only two possibilities. It can be 0 or it has to be the same frequency of arbitrary amplitude. No third possibility. That is the good thing about LTI system. Okay. So in this context, what is the importance of Fourier series? So I am saying here, any periodic signal x of t can be written as a Fourier series. So if x of t is periodic, I can write this as xn e raised to j n omega naught t. Okay. So what this means is, you take nth term and feed that to an LTI system, e to the power of j n omega naught t, impulse response is h of t, I can compute h of s from here, then output will be e to the power of j n omega naught t, output is e to the power of j n omega naught t, same frequency will come out, right. That is because it is an LTI system and this is its eigenfunction. Then the scaling factor will be, frequency now is j n omega naught. So j n omega naught. So substitute s equal to j n omega naught, calculate or evaluate this integral, that is the value of this. So input output is identical except for a scaling factor. Okay. So if x of t is periodic, then the Fourier series theory says I can write it in this form. If I feed each individual complex exponential, I get each individual complex exponential at the output with appropriate scaling factor. Because the system is linear, I can now apply a combination of these complex exponentials. Output will be xn h of j n omega naught e raised to j n omega naught. This is the output. Extremely simple. So for an LTI system, if you feed a periodic signal in the Fourier series form, I know the output already. I don't need to calculate. Right? I know xn serves as a scaling factor, comes out as it is. The actual frequency e raised to j n omega naught t comes out as it is. Just evaluate h of s at s equal to j n omega naught. Substitute s equal to j n omega naught, evaluate and put down that formula. So this is the output. So the beauty of eigenfunctions of LTI system is same frequency comes out. So Fourier series consists of same frequencies, so they come out. So that is what I have tried to capture here. If xn is the sum, then appropriately scaled by h j n omega naught comes out. So the response yt is also some form of Fourier series, because this is a Fourier series, and remember this is now yn, the Fourier series coefficient of y of t. X of t periodic input to LTI system, y of t will be periodic with the same fundamental frequency, and the new Fourier series coefficient yn can be expressed in terms of the individual Fourier series coefficients xn and the scaling factor given by hs evaluated at s equal to j n omega naught. So input periodic, output also periodic, same frequencies. That is a consequence of all this, and that is the reason why Fourier series is so important in the study of LTI series. Okay, so one example application of this interesting application, then we move on to the other questions asked, which is the Fourier transform. Okay, so this is just an example. I am not going to solve this here. I want you to solve this yourself. I will just skim over, right? I will just look at the top interesting points and skip all the details. I want you to supply all the details. Go home and work on this. So I have x of t equal to sine t. That is the input, sine t. So let me sketch sine t. Sine t is an everlasting sinusoid. It is initially 0, sine pi is 0, sine 2 pi is 0. So this fundamental frequency is 2 pi. Sorry, what is it? Sorry, 1. In this case, fundamental frequency is 1. Period is 2 pi. Sorry, period is 2 pi. T naught is 2 pi, f naught is 1 by 2 pi, and omega naught is 1 radians per second. Okay. So this is as simple as it can get. X of t is shown there. What I do is I input x of t into a full wave rectifier. Okay, so this is not an LTI system, it is a full wave rectifier. So output, I don't know what I've called the output as. Okay, I think I've called the output as y of t, shown there. okay, y of t will look something like this. Positive part is as it is 0 to pi, negative part becomes positive, right, 2 pi, positive part remains as it is, negative part becomes positive, and so on. So this is y of t, the fully rectified sine wave. Okay. You see that for this the period was 2 pi, but for y the period is pi, half of that. So because the period is half, its fundamental frequency is 2 times. We will see that, meaning all odd terms will have to be 0 necessarily, right. In this case, because this is period is pi, whereas period here is 2 pi, right. So the fundamental frequency of this and the fundamental frequency of this have a relationship of factor of 2. Okay, so we'll come to that. So so I said, if this is omega, if the frequency here is 1, right, what is the frequency here? What is the fundamental frequency of the output? Remember, output T naught is pi, and so F naught is 1 by pi, and so omega naught is 2 pi, F naught is 2, right, is 2 radians per second. Period became half, fundamental frequency became 2 times, because period and fundamental frequency have a inverse relationship. Going from here to here, period is reduced by a factor of 2, going from here to here, fundamental frequency increased by a factor of 2. Okay, so this is periodic. So y of t can be written as Fourier series coefficient yn e to the power of j 2, that's omega naught nt. So I can compute yn. So you can show that yn is given by 2 by pi 1 minus 4n square. Okay. I am not showing the details. This is not a class for that. So please go ahead and show this. Yn is 2 by pi 1 minus 4n square. So you substitute n equal to 0, n equal to 0. So you have a certain DC term here. N equal to 0 is 2 by pi. N equal to 1 is, this becomes minus 3. So it's 2 by minus 3 pi. Minus 1 also is the same value. Plus, then if you substitute 2, then 2 square is 4. 4 into 4 is 16. 1 becomes less and less important, right? So it's always negative. For n, right, greater than 0, right, this is always negative. Okay, so you can sketch that when you make it take its magnitude, it's positive, and phase also you can extract, it will be pi. So I can now compute yn for that. That's easy, you can do it, no problem. Okay, so what I do is I make this into an electrical engineering problem. This is y of t, right? I feed this y of t into an RC circuit to get z of t. This is a very crude power supply. For those of you, teachers sitting in the audience, you will see that, when it is increasing, the capacitor gets charged. When it is decreasing, capacitor stays there, and it goes on. So you have a very crude stabilized power supply. So this fully rectified wave y of t is given to an RC circuit. That's what I'm trying to show here next. So my value of R, for some reason I selected 15 ohms. Value of C is 1/5 of a farad, very big capacitor. 1/5 farad is a big capacitor, and I want to find out what will be Z of. First of all, realize that in this circuit, this is an LTI system. At least ideally, do not change their behavior with time. So it's time invariant, and I want you to show that this circuit is also linear, meaning it satisfies homogeneity and additivity. So, this is a linear time invariant system, and if you substitute a periodic signal which can be written as y of yn is to j n omega naught t, omega naught being 2 here, output z of t is of the form Zn e to the power j n omega naught t, omega naught is 2. That you can show with your eyes shut, because it is an LTI system and I am feeding complex exponentials. So, output is in this form, and you also know that Zn is yn h j n omega naught. This also I know, this also I know from whatever we discussed before. So, I already know yn, I just have to find out what will be h of j n omega naught for this LTI system. If I know this, Zn is completely known. Is that okay? So, I will solve that and then we will take a small break before we move on to the next topic, which is Fourier transform. Okay, so I have solved it here. I have taken a lot of liberties because I have not defined how to calculate transfer functions. In this case, you can calculate transfer function h of j omega, or in this case I have written it as h, yeah, okay. So, it is this impedance by the total impedance, that is a transfer function. So, this impedance is 1 by j omega c. So, 1 by j omega c is 1 by j omega and c is 1 by 5 by the total impedance, which is 15 plus 1 by j omega 1 by 5. So, that is it is 1 by 1 plus j3 omega. That is what I have shown there, right, in the slide. So, the transfer function is 1 by 1 plus j3 omega. By writing the transfer function as a ratio of this impedance by the total impedance. So, this impedance 1 by j omega c divided by r plus 1 by j omega c, and simplify it, because 5 and 15 have a relationship with a factor of 3, you end up with 1 by 1 plus j3 omega. I said Zn is yn, yn we got it as 2 by pi 1 minus 4n square, this is yn, right, and 1 by 1 plus j. So, in place of omega substitute n omega naught is 2, so it is 2n, right. So, it is 6n, that is Zn. Once we have this, I know the output of this, output of the circuit is Z of t is Zn e to the power j 2nt. For this complicated looking sinusoid becomes full wave rectified, full wave fed to this RC filter, you get this relationship. If you want, you can substitute it as 2 by pi, or is it pi or pi square? Okay, pi 1 minus 4n square, 1 by 1 plus 6 jn, 1 by 1 plus 6 j6n e to the power of j 2nt. That's complete expression, output of the full wave rectified signal fed to this RC filter, right. So, I said this is more like a stabilized output. I am interested in finding out what is the DC value. DC value is, what is this for Z0? This is your Zn, right. What is the value of Z0? Z0 will be n is 0, so it is 2 by pi, and so 2 by pi is, pi is 3.14, so it is approximately 0.6, so it is 0.637 volt. This was 1 volt, you can see that this peak was 1 volt. So, when you full wave rectify this and feed it to an RC circuit, certain value of R, certain value of C, you get DC equal to 0.637, and lots of other things. In circuits it is called ripples, right, in circuit it is called ripples. So, 0.637 of DC combined with lots of ripples, and circuits people really worry about how to control the ripples, right. Given your understanding of Fourier series, you can find out how much power is there in the ripples. So this is the signal for n equal to 0. You find out how much power is there in n equal to 1, 2, 3, 4, minus 1, minus 2, minus 3, and compare the powers. Okay. So it's a good exercise to find out what happens to the power. How much power is there in DC that's useful for your electronic circuits, and how much power causes damage, that's in the ripples. And so such analysis can be carried out because we assume that the circuits are linear time invariant and complex exponentials are its eigenfunctions. Okay, so I'll take a short break. Please ask me questions. After this, I'll just introduce Fourier transform and close for the day. We'll come back next Monday and continue with this. Right, so time to take a good break for questions. So there's one question: how do you measure maximum power for LPF? I don't understand the question. How do you measure the maximum power of LPF? I think LPF is low pass filter is what I think the questioner is implying. I don't have a low pass filter here. Well, my RC is a low pass filter, right? So think of RC as a low pass filter that will filter out all the higher frequencies. So the ripples will be reduced. This is the additional factor on this. So this will weigh these coefficients for an additional factor. So the ripples will be less. How do I calculate the power? I don't know. I mean, you can find out now if this is Zn. So Zn square gives me the power. So that will be 4 by pi square, 1 minus 4n square and 1 plus 36n square under root. Power a square, right? Okay, no under root. 36n square. This is the power in the nth harmonic. Right? This is the power in the nth harmonic. So I can calculate the power in every frequency for n positive and negative. Go on calculating, right? And you can see that the power reduces as n square into n square. So n to the power of 6, very rapid decrease. So you don't need more than 4 or 5 terms, after which this will go to, it will nearly become 0. It will be nearly 0 for n equal to 4 and all, it will be nearly 0. So there is power in the fundamental frequency n equal to 1, maybe n equal to 2. By the time n becomes 3, it's gone to 0 completely, or nearly so. So it's possible then to calculate the power in various frequencies, and I think if that's a question, if I understood you correctly, that's my response to that. PhD Tech, can LTI system introduce phase shift to the input signal? Of course it can introduce, right? Remember, I have here a complex value. A complex value means phase and magnitude, right? I've not talked about phase, so phase shift is inherent. It's possible that you can feed sine, output will be cosine, right? That's possible. 90-degree phase shift is very easy to get. Okay, another question from TCE: whether Gibbs phenomena occurs for a periodic triangle signal. I think Gibbs studied this for a rectangular pulse. I think only in the rectangle. Lot of things are common between rectangular pulse and triangular pulse, meaning it's not differentiable everywhere in the period. A rectangular pulse has discontinuities. Triangular pulse, at wherever they meet, you can't differentiate there, right? So that part is common. Okay, so whether it exhibits Gibbs phenomena, I don't know. I mean, Gibbs phenomena is basically that the peak value, right, in that summation series where you take more and more terms, the peak is some 5 or 6 or 8% of the, is more than your actual value. Here the actual value was 1 and the peak is more than that, right, no matter how many terms you take, and Gibbs showed that. So in that sense, Gibbs phenomena is it refers to the peak value exceeding the actual peak, the peak of the summation. He didn't study this for triangular, maybe a triangular also some kind of a relationship holds good like that. So I've done all this now for periodic signal, right? I assumed input is periodic, and if it's periodic, I can express it as Fourier series, and if I express it as Fourier series, then I can exploit the eigenfunction property of LTI to find out the output, right. So for using eigenfunctions, exponential form is useful. I told you my interest is not computing Fourier series as it is. If you're interested in Fourier series, then you probably want to compute trigonometric form. My interest is in computing the eigenfunction, so I express it in the complex form e to the power of j n omega naught t. There are problems and there are opportunities, right. So advantages are in the exponential form, I can directly invoke eigenfunction relationships. That's the big advantage. And in the exponential form, multiplication and all similar manipulations becomes easy. You know that when you multiply sine and cosine, you have to remember all those trigonometric relationships. You multiply cos and cos, you know, sum and difference frequencies show up, and it's a big mess, right. So whereas manipulation with exponential is quite easy, right. So there are two advantages of exponential form: direct application of LTI as eigenfunctions and easier manipulation. The disadvantages are xn can be complex, right, whereas an and bn for real you know, they will never be complex, and once xn becomes complex, visualizing them becomes more difficult. So there is a problem of visualization, right. I mean, now because it is complex, I have to look at it as magnitude and phase. This problem never occurs in trigonometric series. The question then is okay, this I have LTI systems, I have eigenfunctions. If x of t is periodic, I can use eigenfunction analysis quite well. But what if my signal, what if my input x of t is not periodic, right? Can I still use any of this? You know, all the stuff that we have been talking about for the last 2 to 3 hours, is it useful at all? That is a question, right. So that leads to the idea of Fourier transform. Can I extend the ideas of Fourier series, the ideas of eigenfunction to non-periodic signal? Okay. So I have now shown an x of t. X of t is defined between some t1 and t2. For all other values, it is 0. So it is not periodic at all, right. So it is not, you know, it's that's it. It's defined between t1 and t2. Some arbitrary value. I have only shown positive. It need not be positive, right. So the question is, can I extend the ideas of Fourier series, the ideas of eigenfunction to include signals that look like this, and that leads us to the study of Fourier transform. So that is the second subtopic under frequency domain analysis. Fourier series is the first, Fourier transform is the next. So what I do is, in place of x of t, right, if you look at what I have shown here, I have x of t, right. If you see here x of t, I now build a function called x t naught of t by repeating x t's every t naught second. Okay, t naught is large enough to cover the entire t1 t2, right. So I take this signal x of t and repeat it in both directions in time every t naught second. T naught is completely arbitrary, t naught is left to me, right. And so I have now shown how it will look if I repeat it, right. So this was the original x of t. I have now repeated it infinite number of times, positive and negative. So x t naught is periodic. Because x t naught is periodic, all that I talked about Fourier series applies to that. It is periodic, right. So it can be expressed as a Fourier series expansion. I can use it as eigenfunction and everything. All the ideas apply. So that is what I have tried to capture here. X of t naught can be written as Fourier series, and its fundamental frequency is a 2 pi by t naught, and so on. And I know how to calculate xn's, right. So known problem, right, can be solved. I now introduce couple of more definitions. I introduce a definition of x of omega, right, in the form of x of t e raised to minus j omega t. So let me erase all this and start afresh. And today I'll just introduce. I'll come back and talk about this next Monday. So I now define x of omega with some definitions. Okay, I not very clear why I should define it like this, but I'll come back and talk about why it should be defined. Minus j omega t d omega minus to plus infinity, right? And if you recall, xn of the periodic signal was defined as 1 by t naught integration over t naught, right, x of t e to the power of minus j n omega naught t dt, sorry, this is dt. Compare the two definitions. This is what I know from before, this is what I am doing for the first time. Okay. Then you can see there is some similarity. Okay, there is some similarity. So you can see that xn can be thought of as x of, if you replace omega by n omega naught, this is the same. So n omega naught, right, and there is a 1 by t naught here, there is no t naught here. So this divided by t naught gives me this. So xn was defined as this. I am now introducing a new definition. So I am connecting up xn with this. Okay. So and so that is a starting point of going from Fourier series to Fourier transform. Maybe I'll just do one more slide and then go today. Right. So for some t naught, I can calculate. This is the continuous function of omega, right? Because omega takes all values from minus to plus infinity. So let's say I sketch x omega and look something like this. Let's say I make it, I divide by t naught also, so just a scaled version, and xn is sampled versions of this. So this is omega. Now this is some omega naught, 2 omega naught, 3 omega naught, and so on, minus omega. Okay. So for some t naught, I can calculate xn by sampling this function at multiples of omega naught. Okay, that's one idea. Now if you go back, I am repeating x every t naught seconds, and t naught can be anything, right? What if I increase the period, instead of putting them so close by, what if I make my t naught larger, t naught is bigger, right? That means between one pulse and the second pulse there is a large gap, right? By increasing t naught, I am increasing the gap between them. So that's, so if I increase the gap, then omega naught is 2 pi by t naught becomes large, omega naught becomes small. So the points move closer, right? T naught becomes large, so this becomes smaller. So it is possible then that I have x omega remains the same, by now I made it 2 t naught, so it is half the size, not as tall as this but shorter, but omega naught also reduce, so the points move closer together. The omega naught, 2 omega naught were apart, because I made t naught bigger, omega naught becomes closer. That is the point I am trying to say here, right? So you can now go on increasing t naught, and these pulses move closer and closer and closer, and finally they become dense, right. This height reduces and then it becomes infinitesimally small. So points become dense and the height becomes very small because T naught becomes very large. Okay, so that's what is said, and so with that you can show this leading to new definition, because remember x of t in the Fourier domain was written as xn e raised to j n omega naught t, right. Xn is x n omega naught by t naught e raised to j n omega naught, right, and t naught becomes very large, right, which means omega naught becomes very small. If you use that, in the limit summation becomes an integration, right, integration, and T naught is very large, so 1 by T naught is infinitesimally small, so you get x omega e raised to j n omega, sorry, omega t and d omega, because 1 by T naught is extremely small, so it is d omega. So that is the relationship now between xt and x omega. So I have a pair of relationship. I'm in a hurry, so I'll come back and do this again next week. I didn't quite explain how the 2 pi comes in. So I have x of t as 1 by 2 pi x of omega e raised to j omega t d omega. Okay. I'll come back and talk about this next time. Maybe we'll stop here. If there's some 1 or 2 questions, I'll be happy to take, right, and then we close for the day. Okay, so there's a question from CIT. It says whether the convolution property satisfies the Fourier series. I don't know what is the meaning of convolution property satisfying Fourier series. Fourier series is different, convolution is different, right. Fourier series applies to periodic signals, convolution applies to LTI signals. So convolution should, there is no need for convolution to satisfy any Fourier series property. Okay, so I don't quite get the question. Fourier series for full wave bridge rectifier is a sine or cosine waveform. You know, sine and cosine are identical waveforms except for phase. That's the point I made earlier, right. So you can have a you can take sinusoid and full wave rectify it. You can take a cosine and full wave rectify it. I mean, final answer is the same, right. I mean, except for some phase difference, answer is the same. So the Fourier coefficient will have an additional phase term. When you take its magnitude, that term just vanishes, right. And so sine or cosine doesn't really matter. Is convolution possible for non-LTI system? Since non-LTI systems have impulse response? No, right. First of all, convolution is defined only for LTI systems, right. That is the point we made in deriving the result convolution. We used the features of linear and time invariant. Okay, so first to answer your question emphatically, no, right, only LTI systems have convolution. Then the second question is other systems also have impulse response. Okay, I have to differ with that statement, right. We defined impulse response in a very narrow sense, right. We said when the system is LTI, when an impulse is applied at time t equal to 0, the output is h of t, only that is called impulse response, right. An impulse response assumes an LTI system, right. Just because to any system you can give an impulse and some output comes doesn't mean anything, right. That is not very useful thing at all. So impulse response makes sense only when the system is LTI, right. Only for LTI systems I can write convolution in terms of input and impulse response, right. And so please, you know, disabuse your mind from the thought that any system can have impulse response. that is not the true, right. We have defined impulse response in a very narrow way. Only for LTI systems, when I apply delta at the input at time t equal to 0, the response is called impulse response. If it is not LTI, there is no impulse response. I will come back to it. I'll come back to this, right. Both questions deal with Fourier transform. I just started Fourier transform. I will come back next Monday and answer those questions, right. Thank you.